Before a single drill bit ever touches the seabed, before a massive platform is designed, and way before a pipeline route is even planned, someone has to actually find the oil. And honestly, that is exactly what this explainer is all about. We're diving into the incredible, high-stakes detective story of how we locate energy reserves hidden miles beneath the ocean floor. It's a pretty wild question when you really think about it, right? How do you find hydrocarbons locked away in solid rock, buried under thousands of feet of dark, heavy ocean water? Well, before anyone drops tens of millions of dollars, someone has to play the role of an underwater detective. We have to map out an environment we literally cannot see, relying on some brilliant science to secure the energy that powers our world. So let's kick things off with Section 1. The search begins. To solve this mystery, we first need to understand the absolute backbone of the industry for the last 50 years, seismic surveying. The crucial thing to grasp here is that this works on a fundamental physical principle. It's actually a lot like a giant geological ultrasound. We're sending energy deep into the earth and very carefully listening to how it bounces back. This brilliantly illustrates the physics at play. You see, sound waves travel down through the ocean and penetrate the rock beneath. And when those sound waves hit a boundary between two completely different types of rock, let's say a layer of sandstone sitting right on top of a layer of shale, some of that energy bounces or reflects back up to the surface. By recording the exact timing and the amplitude of those returning echoes, geophysicists can actually build a picture of the underground rock structure. Moving right along to Section 2, making waves, marine surveys. Out on the open water, the specialized gear they use is just massive. What you have is an array of air guns towed behind a survey vessel. These guns suddenly release compressed air to create a highly controlled pressure wave. It's essentially a controlled underwater explosion, but without any actual explosives. And trailing far, far behind those air guns are the hydrophone streamers. These are the massive cables designed to catch all those returning echoes. Just to help you wrap your head around the sheer scale here, a single survey vessel might tow anywhere from 8 to 12 of these streamers, and each one of these cables can stretch 6 to 8 kilometers long. That is literally miles of sensors trailing in the water. You can think of the air guns as the detective's magnifying glass, and the thousands of sensors on those massive cables as the notepad, recording billions of data points. And again, absolutely no dynamite is used here, just compressed air. All right, part 3, seeing underground, and how we went from 2D all the way to 4D. In the early days, we had to rely on 2D seismic surveys. They shot in parallel lines, giving us a flat, two-dimensional cross-section. It gave a decent big picture view, but honestly, it had terrible cross-line definition, leaving geologists drilling somewhat blind. But then the leap to 3D seismic in the 1980s was a total game changer. By shooting a really dense grid, we created a complete 3D data volume. Suddenly, geologists could slice this data cube in literally any direction, horizontally, vertically, you name it, allowing them to drill with so much more confidence. And building on that, we now have incredible time-lapse 4D seismic. Basically, this involves repeating that exact same 3D survey over the same area years later, usually after a field has been producing for a while. By comparing the differences, engineers can actually watch seismically how the fluids are moving within the reservoir. They can literally see the oil draining from the rock over time, which helps them figure out exactly where to place their next wells to grab any bypassed oil. Which brings us to Section 4, setting the trap. Once those billions of data points are collected, this is the kind of stuff our scientific detectives are staring at on their screens. They use complex algorithms to process out the noise and correct the image. What they're desperately searching for are geological traps. They want to find specific places where porous reservoir rock is capped by a perfectly impermeable seal, something like cemented sandstone or salt, that absolutely stops the hydrocarbons from escaping upward. The most classic textbook clue they look for is the anticline. It's this dome-shaped fold in the rock where oil and gas naturally migrate upward and pool together. But, and this is super important, we're not talking about massive, hollow underground caverns here. The hydrocarbons actually sit within the microscopic pores of the rock itself. It's very much like a hard sponge holding water. Beyond the anticline, things like fault traps, stratigraphic traps, and salt domes are other prime suspects they look for. Once a potential trap is spotted, the workflow becomes incredibly rigorous. The geologists map out the structure, assess what they think the rock quality is, and calculate just how large the accumulation could possibly be.
Then, they generate a probability-weighted estimate of the potential resources. And notice I emphasize probability, because even at this highly advanced stage, they are dealing with a distribution of possible outcomes, definitely not a guaranteed single number.
And that leads us right into our final section, Part 5, the million-dollar gamble. Here is the harsh reality. Despite supercomputers and literally billions of data points, sound waves alone cannot confirm the presence of oil. To truly know if hydrocarbons are actually down there, you have to drill an exploration wildcat well. And this is a massive, massive undertaking. It takes about 8 weeks and costs up to $10 million. And if you're operating in extreme environments like Arctic waters, that cost can easily skyrocket to $60 million just to take a look. So here is the dramatic climax of our whole detective story. Historically speaking, only about 1 in 10 of these extremely expensive exploration wells actually results in a commercial discovery. Let that sink in. Even with the absolute best 3D seismic data in the world, the trap might just be full of water. Or maybe the oil is there, but the rock quality is just too poor to flow. Or maybe the discovery is just too small to be economically viable. It's a massive gamble. Because exploration is fundamentally such a probabilistic business, no single well is ever a sure thing. Oil companies manage this insane level of uncertainty by exploring in portfolios. By spreading their risk out across many different prospects and geological traps, they ensure that the rare, massive successes can ultimately pay for the inevitable, very expensive failures. So as the easier-to-find fields dry up and we're forced to push further into ultra-deep water and incredibly complex geological environments, it leaves us with a really compelling question. Just how far will this incredible seismic technology have to evolve to keep solving these high-stakes mysteries of the deep ocean? It's a fascinating challenge, and one that the industry's top minds are tackling every single day. Thanks for joining me on this explainer, and I'll catch you in the next one.